All right. Hopefully my voice is in here. Let's get started. So today we are talking about 2.6. We're basically talking about asymptotes. That's the focus of today. Asymptotes are related to a bunch of definitions of different limits. So let's get a feel for asymptotes real quick, and then we'll go over the precise definitions, then we'll do a bunch of examples. That's all we'll be doing today. So first off, you've been dealing with functions where you factor the numerator and the denominator, and you get the same term in the numerator and the denominator, right? Mm-hmm. And what happens when you have the same factor in the numerator and denominator? What does that mean about your function?
It has a hole there.
It has a hole there. And it has a hole wherever this is 0. So if we look at the function x squared minus 1 over x plus 1, well, this is the same thing as x plus 1 times x minus 1 all over x plus 1. Right? Notice how this factor cancels out with this factor. So this function would have a hole where? Minus 1. So at x minus 1, this function, whatever it looks like, over here at minus 1, it has a hole for however the function's going. Okay. So when it's a factor that cancels out top and bottom, then we're talking about a hole in the function. With me? Yeah. Now, let's pretend that we had something like this. So fix this head, I guess. X squared minus 2x plus 1. Excuse me. Okay, so now, notice when we factor it, nothing cancels out. Right? Mm-hmm. So now, where the denominator 0 is a vertical asymptote. So now, for whatever this function looks like, there's a vertical asymptote at 1.
At negative 1?
At negative 1, yeah, sorry. The number that makes the denominator 0.
Oh, okay.
Make sense? So if it cancels out, we're talking about a hole. If it doesn't cancel out, then there's a vertical asymptote wherever the denominator is 0.
What exactly is an asymptote?
It's a line the function approaches, but never actually reaches. So let's plot one that we're pretty familiar with. If we look at the function 1 over x, notice I can't cancel out that x with my numerator. Right? So where is the denominator 0?
Just a 0.
Just a 0. So when we graph this function, then your y-axis is also an asymptote. So when you graph this function, it looks like this. And so the line shoots up to infinity here, never quite reaching the y-axis.
So with an asymptote, the function never really crosses it.
It never crosses a vertical one. It could cross a horizontal one. It's just what it's getting closer and closer and closer to as it gets higher and higher values.
That would be considered an odd function.
Yeah, this function is also odd. But as we get closer and closer to 0 from the right, our function gets closer and closer to infinity. As we get closer and closer to 0 from the left, our function gets closer and closer to negative infinity. So when your function is shooting up or down to infinity is when you have a vertical asymptote. We'll do the precise definition here in a sec.
Okay.
This is just intuition and algebraically what you're looking for. With me so far?
Mm-hmm.
Yeah.
So we talked about a hole, we talked about a vertical asymptote. Now we have horizontal asymptotes or oblique asymptotes. A horizontal asymptote is exactly what you think it is. It's just a horizontal line now. An oblique one is one that's just not horizontal or vertical, so it's just not slanted.
So it can have a slope?
So it has a slope, yeah.
Okay.
So all asymptotes are just lines. If it's a vertical line, the asymptote's vertical, we call it a vertical asymptote. If it's horizontal, we call it a horizontal asymptote. If it's neither, we call it an oblique asymptote.
What
Okay.
does horizontal look like in algebra?
We'll see examples when they all come up.
Okay. And an oblique one as well.
Yeah, we'll see one of each. So now, let's say that we've got our function f of x here, and it's a rational function, so polynomial over polynomial. Now, we call the biggest n that shows up in this polynomial the degree of the polynomial. So for example, x cubed minus x to the 5 plus 6, this is a 5th degree polynomial.
Okay.
Because 5 is the biggest exponent that shows up.
Okay.
If you write your polynomial out like this, n is the biggest degree exponent that shows up, so this is an nth degree polynomial. With me?
Mm-hmm.
And this is an nth degree polynomial. So two polynomials. Maybe they're the same degree, maybe they're not. Maybe this one's bigger degree, maybe this one's bigger degree. We're going to look at all the cases we're interested in. So, three things to look at. If m is bigger than n, then it has a horizontal asymptote at y equal to 0. So if your denominator is a higher degree polynomial than your numerator, it has a horizontal asymptote at y equal to 0. Once again, should have left this up there. F of x equal to 1 over x. What's the degree of the denominator? 1.
1.
What's the degree of the numerator?
1.
0.
Yeah, 0.
Because you could view this as 1 times x to 0 for 1. Still the exact same thing.
Mm-hmm.
So, the denominator is a higher degree than the numerator. That means this thing should have a horizontal asymptote at y equal to 0.
Horizontal?
A horizontal.
But in your picture it was vertical.
Well, we have both. A function you can have multiple asymptotes.
Okay.
All the asymptote was as it was approaching the x-axis.
So we knew when's the denominator 0. That gives our vertical asymptote right here, right?
Yeah.
But then we know since the denominator is higher degree than the numerator, it has a horizontal asymptote at y equal to 0 here.
Okay.
So now when we graph our function, once again, it looked like this. Right?
Mm-hmm.
Yeah.
So with horizontal asymptotes, what we're saying is, as our function becomes arbitrarily big, it gets closer and closer to this line, or as our function becomes arbitrarily small, meaning real far in the negative direction, it gets closer and closer to this line. Horizontal asymptote.
Okay.
Okay. So if m is greater than n, you have a horizontal asymptote right at y equals 0. If m is equal to n, then you have a horizontal asymptote at the ratio of their coefficients. So let's look at an example of that.
Yeah.
So if I have f of x is equal to 5x squared plus 2 all over 3x squared minus 5x plus 7. No clue what that function looks like, right?
Mm-hmm.
But what do I know about it?
That they both have the same exponent.
Since that exponent and that exponent are the same, then whatever this function looks like, when we plot it, here's the line 5/3. I know that 5/3 is a horizontal asymptote for this thing.
Oh, so it's only the coefficient for the highest one,
The
right?
coefficient of the highest order terms. Yep.
Okay.
So it's a sub n over b sub n. Notice a sub n was the coefficient of the highest degree term, and b sub n was the coefficient of the highest degree term.
Okay.
Good?
Yeah.
Okay. Now the last case is when the numerator is 1 degree higher than the denominator. If it's more than 1 degree higher, we don't say anything about it. We can't conclude anything about it. But if it's only 1 degree higher, the numerator is only 1 degree higher, then you have an oblique asymptote. So this is going to be an asymptote that's slanted somehow. And how do you find that asymptote? You do this divided by this, and then you ignore the remainder. So you've done division with polynomials before. It's probably just been a long time. So you have to do something like 5x cubed plus 0x squared. I'm not going to do it with this example. The math will probably come out here, so we'll wait till we see an example.
Okay.
But the point is, when I divide this out, I'm going to get something like, I'm just throwing up numbers, none of this is honest. I'm just going to get something like 3/5 x plus 2 plus some remainder all over 3x squared minus 5x plus 7. So if I did my division, I'd get 2 terms with a remainder of something. Ignore the remainder, graph this line, that's your oblique asymptote.
Why do you ignore the remainder?
It makes no difference for really big numbers. because this whole thing will go to 0. All this will make sense.
Okay.
But that's your telltale things that you watch for. So that's pretty much what you're going to memorize when you're working with functions. And then how it all makes sense, we'll go back and fill in. Okay. With me?
Mm-hmm.
Okay. So now we'll just tackle it in order the book introduces stuff. Just wanted to give you a high-level picture first. Okay, example 1. Example 1 says, show that the limit as x approaches 0, or x approaches infinity, of 1 over x is equal to 0. So that means that they introduce definitions first. Okay, so covering the material, the order that the book does. So we're going to introduce 2 different types of limits now. There's still limits in the sense that we've been taking limits this whole time. It just slightly changes the definition for these different cases. So now we're going to define this symbol. What does it mean to take the limit as x approaches infinity of f of x? Or what does it mean to say the limit as x approaches infinity of f of x is equal to L? Intuitively, what that means is whatever our function's doing, here's L, whatever our function's doing, as we take off to infinity, we're getting closer and closer to that number L.
Okay.
So you can see how this is related to horizontal asymptotes.
Mm-hmm.
Right? So that's intuitively what it means. Now let's read the definition. What does this mean? It means for every epsilon you pick around L, so pick any teeny value around L you want, I can always find some supermassive number, clear out here, we'll just pretend it's right here. I can always find some supermassive number n, such that from n onwards, this function is always within this distance.
Okay.
So you pick some small distance around L. I'm saying I can show you that if you go far enough down this thing, you'll be within that distance of L. If I can always do that, then this thing approaches L, or the limit as x goes to infinity is L. That's intuitively what it says. So let's read the exact definition. This is the case. What does this mean? It means for every epsilon, every distance around L, there exists some m, some really big number, such that if x is bigger than that really big number, if we've gone way down there, then the distance between f of x and L is less than epsilon.
L being the isotope?
L being right here, the value that we're saying the limit approaches.
Yeah, the isotope, right?
The asymptote would be y equals L. It would be that line. L is just a number. Y equals L is the line. So, slight difference.
Oh, okay.
Make sense?
Yeah.
Okay. Then this next definition is identical, but going the other way. So now we're talking about our picture is going to look something like this. Here's L. Our function is going to go like this. So for any epsilon, we're saying there exists a negative m such that if you pick x's after this negative m, smaller than this negative m, then their corresponding position on the function, f of x, is within epsilon of L. Okay, so that's what this says. So let's read it. The limit as x approaches negative infinity of f of x equals L is logically equivalent to, for every epsilon, every positive number epsilon, there exists some really big number n, such that, some really negative number m now, such that x being less than m implies the distance between f of x and L is less than epsilon. See how it's almost identical?
So in the formula, when you substitute the m for a number, it's always a negative number?
It doesn't have to be a negative number. Like if you, so let's pretend our function was this. It's just typically a negative number. Same way, epsilon doesn't have to be a really small number. It's just that's how you think of it. So for example, you could have a function that does this. Here's our L. And your function might do this. and you might pick some big epsilon around L, like this. Then I say, okay, so m, starting right here, m, you pick any x's less than m, which could still be positive, then this is true. It's just typically, when you think about it, you think about a really big negative number. And epsilon you think about as being really small.
Okay.
So it doesn't have to be, but notice that if it's true for a positive number, then it will be true if you picked a negative number as well.
Yeah.
Because if you were within epsilon from here, you would definitely be within epsilon from here. Okay. So you can arbitrarily make that one positive and or this one negative and this one positive. If it's true for all numbers less than a positive number, it's definitely true for all numbers less than a negative number. And if it's true for all numbers greater than a negative number, it's definitely true for all numbers greater than a positive number. So you can always think about this as being positive and this as being negative, and it works. Make sense?
Yeah.
It just might be in a problem if they have you actually calculate one. If it came out positive, not a problem. Okay. So now, horizontal asymptote, the exact definition. The line y equal to b is a horizontal asymptote provided that the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b. So as a function, if you plug in values really far to the right or really far to the left and keep getting closer and closer to the line, we call it line an asymptote. Horizontal asymptote. Does that make sense?
What if it hits B? Like, never mind.
I'll give you a really good one to give you a sense of what it is exactly that you're saying. Think about the function 1 over x times sine of x. So here's a pretty weird one, right? Because what does the sine function do by itself? It oscillates, right? But when you do 1 over x, notice that this is making the amplitude of the wave smaller and smaller and smaller. So as x gets bigger and bigger, now what's happening is this thing looks like this. Right?
Yeah.
And it's getting closer and closer to what?
0.
0, right? If I plug in a really big x here, like 1 over something like that, times, well, the biggest sine can ever be, doesn't matter what you plug in, is 1, and the smallest it can ever be is negative 1. So if you times it by 1 or negative 1, you still get a really, really small number.
Okay.
Make sense? So this gets closer and closer to 0, so that would be its horizontal asymptote. Notice it also crosses it an infinite number of times. So you can cross horizontal asymptotes, nothing wrong with that. Your vertical asymptotes you can't cross.
Why is that?
Because your vertical asymptotes happen where your denominator is 0 and your function is not defined there.
That makes sense.
Huh.
Okay. So now let's jump into some of the author's examples. What does he want me to do? I think I'm proving this is the case. Show that by using the definition of curve. So let's do this proof real quick. First example he does is a proof that the limit as x approaches infinity of 1 over x is equal to 0. Right?
Okay.
So 1, let epsilon greater than 0 be given, assuming that I'm given some positive number. What is my job? My job, notice that we're using this definition. My job now is to find an m such that if x is greater than m, then f of x is within epsilon of 0.
Okay.
So I'm trying to find the m such that if m is less than x, that implies that the distance between 1 over x and 0 is less than epsilon. Okay. So my whole job now is to just find this m, right?
Mm-hmm.
Okay, so 2, observe that 1 minus x minus 0 less than epsilon is the same as 1 over x absolute value less than epsilon, which is going to be the same as Since we're going off to the right for arbitrary large numbers, I can ignore any negative x's and just start with the positive ones. For the same reason that we said before. So I can drop the absolute value and say, we're looking for it when this happens. So it will actually be when this is true, this is also true.
I apologize, I don't quite understand the relationship between epsilon and the m.
And, okay, let's draw a picture one more time and come back to this. We are just trying to show that, so our function looks like this in the positive section. Here's what our function is doing. I'm arguing that as x approaches infinity, the entire function gets closer to 0.
That intuitively makes sense.
It intuitively makes sense. So what does that mean? That means that for any epsilon you pick around 0, so here's epsilon, here's negative epsilon. For any epsilon you pick around 0, I need to be able to find an m.
So m is an x.
M is an input, yeah. It's a big number on our x
I'm
coordinates.
with you now.
I need to find an m such that if you pick an x after that m, then, so if I pick an x after the m, then f of x, the height of the point, is within epsilon of 0.
Any number. On both. Okay, yeah, I get that. Yeah.
Okay.
Alright.
Yep. Okay. We will write this out formally. We'll just make it make sense. So we want 1 over x minus 0 less than epsilon. Well, that's going to be, we'll have that when we have 1 over x absolute value less than epsilon, which we'll have when we have 1 over x less than epsilon. We're going to just look at our positive cases now. And notice that this will happen when multiply both sides by x and divide both sides by epsilon, if you want to think about it that way, or flip the reciprocal on both sides, which will flip my sign, whichever way you want to think about it. That'll happen when x is greater than 1 over epsilon. Okay.
You multiply by x.
I can multiply both sides by x and divide both sides by epsilon.
Doesn't that just make x over x, which is 1?
Okay, let's do that. So I'm going to write this. I'm going to multiply both sides by x and divide both sides by epsilon. So I'm going to do multiply both sides by x divided by epsilon on this side. And I'm going to multiply this side by x over epsilon. So this epsilon cancels out with this one. This x cancels out with this one. We're left with 1 over epsilon is less than x. Okay. Makes sense? Okay. So there we have it. That's our m. So now notice if x,
Your m is x, or is
1 over epsilon is less than x, that implies that the distance between 1 over x and 0 is less than epsilon.
Okay.
Notice that epsilon is typically a really, really small number. When you do 1 divided by a really, really small number, you get
A big number.
a really, really big number.
Yeah.
If I do 1 divided by 0.0001, well, that's equal to 1,000, 10,000. No, 1,000, around 10,000.
10,000.
Jeez. Right? So if this was your epsilon, this is your m. Okay. So next one. Notice how similar these are to proofs with limits in general. They're just slightly easier now. Because you're not finding delta, you're just finding an m.
Yeah.
But yeah, they're all very, very similar thinking in how we do all of them. Okay, next they want me to show that the limit as x approaches negative infinity of 1 over x is equal to 0. So last time we did as it approaches infinity is 0, well also as it approaches negative infinity it's 0. So how do we show this one? Almost the exact same way. So we say let epsilon greater than 0 be given. So you pick any positive number you want, I don't care what it is. Then I am trying to make sure that 1 over x minus epsilon, minus 0, thank you, is less than epsilon. So I want the absolute value of 1 over x to be less than your epsilon.
But now we're just
Right.
looking at the negative case, right?
But now we care about the negative case. So the absolute value of 1 over x is going to be negative 1 over x, less than epsilon. If it's true for any positive numbers, less than n, it's definitely true for the negative numbers, less than n. We can always drop off those positive numbers and just focus on the negative cases. We can always go further left, in other words, in this case. Okay, so now we want negative 1 over x less than epsilon. Well, when's that going to happen? Flip reciprocals on both sides, which flips the sign. So we get negative x is greater than 1 over epsilon. Right?
Mm-hmm.
And now, multiply both sides by negative 1. It's going to happen when x is less than negative 1 epsilon. So there's your m. So m equals negative 1 epsilon. So then if x is less than m, that implies that the distance between f of x, which equals 1 over x, distance between f of x and 0 is less than epsilon. See that?
Yep.
Cool. No. For all these new limits that we're defining, all the limit rules that we had for our previous limits still hold with these. So the limit of a product is still the product of the limits, the limit of a sum is still the sum of the limits, etc.
Okay.
Okay, let's do another example. Okay, so now we're just solving it, we're not proving anything. So I'm trying to solve the limit as x approaches infinity of 5 plus 1 over x, and I'm trying to solve the limit as x approaches negative infinity of pi root of 3 over x squared. Okay, let's take these one at a time. I'm sure that you could figure it out. The limit of a sum is the sum of the limits, right?
Mm-hmm.
So what's the limit of 5 as x approaches infinity?
Just 5.
Just 5. 5 in no way depends on x. Change x all you want, 5 is 5. So this is still 5 plus, what's the limit of 1 over x as x approaches infinity?
0.
If you plug in really, really big numbers for x, 1 over x gets really, really close to what? 0. And we just already proved that that was 0, right? So there you go, 5 plus 0, so it's equal to 5.
How would you do that one then?
Well, let's do it. So now this one is equal to, the limit of a quotient is a quotient of the limits. Well, actually, that's just as a product. The limit of a product is a product of limits. So I can view this as the limit as x approaches negative infinity of the numerator times the limit as x approaches negative infinity of the denominator, right?
Okay.
And now we can break that denominator up again into 1 over x times 1 over x.
Mm-hmm.
You with me?
Yes.
So this is equal to the limit. I'm just going to write limit, we'll bother with the underneath stuff. We know what limit we're talking about. So we got the limit of pi times root 3 times the limit of 1 over x times the limit of 1 over x. What is the limit of 1 over x?
0.
0. So this is 0. This is 0. What's this?
0. What?
Well, the whole thing will be 0, but what's this?
I over root 3.
Pi times the square root of 3. It's just a constant.
Oh, yeah.
Limit of a constant is still constant.
That's right.
So you put a constant times 0 times 0 is obviously 0. So 0. Notice, that's very intuitive already. What happens to this whole thing as we plug in bigger and bigger numbers for x? The numerator doesn't change, but the denominator gets really, really big.
Yeah.
And so the whole thing gets really, really close to 0.
Okay.
All right. So now we'll look at the limit x approaches infinity of 5x squared plus 8x minus 3 all over 3x squared plus 2. So we'll look at this limit, and then we'll look at the limit as x approaches negative infinity of 11x plus 2 over 2x cubed minus 1. Good? Okay. Let's just try an intuition test really quick. What do we think this should be approaching?
0.
0? Anyone have a different answer?
So is this the one where we ignore the remainder because there's...
No. But just try to think about it in a logical way. Don't try to make reference to past ideas. What is this going to approach as we plug in bigger and bigger numbers for x? Let's try something really quick. Let's plug in 1,000 for x and see what happens. You with me? So what would we get if we plug in 1,000 for x? Well, we get 5 times 1,000 squared, or in other words, 5 million, plus 8,000 minus 3. What is the numerator really, really close to?
5 million, 8,000.
5 million. That's what it's really close to.
Oh, okay.
I mean, kind of close to it, but yeah.
It's really close to it. We're less than 1% away from it.
Okay.
Right?
Okay.
And let's look at the denominator. What do we have here? We have 3 million plus 2. What's that really close to? 3 million.
And you're saying the...
So what does that equal?
5/3.
5/3.
And they're going to get farther.
And notice the bigger x's we plug in, the more all these other terms don't matter. The only terms that matter are the ones within x squared.
Right.
So only the highest ordered terms matter.
But they completely dominate your fields.
Right, they're called dominant terms. That's exactly what they're called. They're called the dominant terms. They dominate everything else. So intuitively, we come out 5/3. Now, how do we actually show it? We're going to divide everything in the numerator and everything in the denominator by the highest term we see in the denominator. So the highest order term we see in the denominator is x squared. You with me? So I'm going to divide everything in the numerator and everything in the denominator by x squared. Okay? So this is equal to the limit as x approaches infinity of, we get 5x squared over x squared, which is just 5, right? Plus 8x over x squared is just 8 over x, minus 3 over x squared. So that's the numerator. With me so far? Same thing to the denominator, we get 3 plus 2 over x squared. And now we can break this up into a bunch of individual limits. What is the limit of 5 as x approaches infinity? 5. Plus, what's the limit of 8 over x as x approaches infinity?
0.
0. Right? That's the same as 8 times 1 over x. Take the limit of that, you get 8 times 0. Right?
Okay.
So that's 0 minus, what about 3 over x squared? 0. All over 3 plus 0, which is equal to 5/3. Make sense?
That's so weird.
Why did you divide the x squared?
Divide everything by x squared,
Yeah.
so that I either had constants or dividing by x.
Okay.
Because we know how to do dividing by x, that's real easy.
Yeah.
Because of 1 over x?
Yeah, because we already handled 1 over x. Okay, so now let's look at this one, and did I do this right? Yeah. Okay, so what do? We divide top and bottom by the highest order term in our denominator. So x to the highest degree that we have. What's the highest degree that we have in our denominator?
X cubed.
X cubed. So we're going to divide top and bottom by x cubed. So this is equal to the limit as x approaches negative infinity of 11x over x cubed is going to be 11 over x squared. With me on that? plus 2 over x cubed. I think you guys are getting it now, so I'll just go a little bit faster. You follow that? Now we can take our limits. What's the limit of 11 over x squared? 0. 0. Plus, what's the limit of 2 over x cubed? 0. 0. All over 2 minus 0, 0, which is equal to
0.
0. And intuitively, hopefully that makes sense.
Yeah,
If I have 11x over 2x cubed, the denominator is going to grow way faster than my numerator. This thing's going to get really close to 0 really fast.
Okay.
Okay.
Kind of messy. All right.
It'll get to the point where you don't really think about it, you just do it. You'll get to the point where you see that equation, they say 5/3 or 0. That gets pretty easy.
This has practical application in the real world.
Yes.
That's classic.
Yeah, you'll see all the physical application in the real world when we get to physics. Calculus is the most applicable body of knowledge there is in terms of math, because, well, I shouldn't say it because there's math that presupposes, but Newton literally had to discover calculus to do physics. That's what he discovered it for. He was discovering the math he needed to do physics. So all the math that was developed here was for physics.
That's so cool.
That's why we are rushing through calculus really quick to get to physics. And we'll see how, yeah, it just comes up left and right. Okay, so we did those examples. Notice now, really quick, that this, when we look at our haphazard way of talking about asymptotes, the degree of the numerator and the degree of the denominator were equal, right? So it actually has a horizontal asymptote at 5/3. So taking these limits and calculating horizontal asymptotes are the same thing. Notice this one, we had a bigger degree in the denominator than we did in the numerator. So we said this should have a horizontal asymptote at y equal to 0. If the degree in our denominator is bigger than the degree of our numerator, we have a horizontal asymptote at y equals 0. When we calculate this limit, we got 0.
Wow.
So this limit is calculating your horizontal asymptotes. Come back to our definition of a horizontal asymptote. The line y equal to b is a horizontal asymptote provided the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b. Make sense?
Yeah.
So calculating these limits are calculating horizontal asymptotes.
Okay.
You can calculate them taking limits, that's the proper way to do it, but then we come up with these quick and ready rules that are well proven to do it from once you get comfortable with the limits. Okay. Next example. So we want to find the limit as x approaches infinity for x cubed minus 2 minus 2 over the absolute value of x cubed plus 1. And then we'll do the negative case. Limit as x approaches negative infinity. So that same thing, x cubed minus 2 over x cubed plus 1. Okay, so this is equal to the limit as x approaches infinity. Since we're taking off arbitrarily far to the right, we can drop all our negative x's.
Okay.
Right? And so the absolute value of x, if x is positive, is just x.
Mm-hmm.
Right? Absolute value function of x is equal to x if x is greater than or equal to 0, negative x if x is less than 0. Here we're talking about x is greater than or equal to 0, so the absolute value of x is just x. So this is the same thing as limit of x cubed minus 2 over x cubed plus 1. Now hopefully you can tell me right out the door what this is going to equal, just looking at it.
-2.
The limit of this whole thing?
1. Yeah.
It's 1. Yeah.
1. Let's plug in a number one more time to help it make sense. Let's plug in 1,000 to this. With me? What's 1,000 cubed? 1 billion.
Yeah.
Minus 2. All over 1 billion.
Oh, I see it. Yeah, I was thinking about that.
Yeah. So just plugging in a number makes the intuition click so fast. So you get a little bit confused, just plug in an easy number like 1,000, see what's happening, and I think that'll help you most of the time.
Okay.
Okay. So we see that this thing should be getting really, really close to 1, but we'll go through our process of the division. What do we divide top and bottom by?
X cubed.
X cubed, the highest order term in our denominator. So this is equal to the limit as x approaches infinity of x cubed over x cubed is 1 minus 2 over x cubed all over 1 plus 1 over x cubed, which is going to be equal to 1.
Which is a horizontal.
Yes, so this has a horizontal asymptote at a positive 1.
Okay.
Now, let's look at the same function, but take the limit as x approaches negative infinity. What's the absolute value of x when x is negative?
It's negative X.
It's negative x. Keep in mind what the absolute value is. Very common that you get confused by this the first few times, even though it's real simple. Because we don't like seeing a negative attached. We don't like seeing negative x and thinking about it as positive, but it can be because x can be a negative number. So the absolute value of negative 3 is, well, negative 3 is less than 0, so it's negative 3. So if x is negative 3, then its absolute value is negative x.
That's like the opposite of how I would talk about absolute value.
No, the intuition is just hard to retain because you always want to talk about this like it's a negative number. It's hard to take the leap that negative x can still be a positive number. Just because it has a negative sign out there doesn't mean it's not a positive number. Because x itself can be a negative number. So negative can be positive. But this is the definition we were given.
Oh, okay, so it's the absolute value of x by 3, then is it 3 at the absolute value of x times the absolute value of x times the absolute value of x?
Yes.
And then if I put a negative, if x returns a negative, doesn't the absolute value turn it back to positive?
The absolute value of x, if x is less than 0, is negative x. This and this are the exact same symbol when x is a number less than 0.
Why do you put the absolute value in there?
Absolute value is a function. If x were positive, then the absolute value of x is equal to x. If x is negative, then the absolute value of x is negative x, which makes it positive again.
I don't understand.
So, okay, look, let's use concrete numbers. What is the absolute value of 3 equal to? 3. What is the absolute value of negative 3?
3.
No, you're simplifying. It's negative 3. That's the definition. Now negative 3 is equal to 3. That's correct.
Oh, okay.
But now replace your negative 3's with x's. So get rid of that, replace your negative 3 with x. The absolute value of x is equal to negative x, when x is a negative number.
Oh, wait, okay, what? Let's say the last part.
Look, the absolute value of negative 3 is equal to negative 3, right?
Okay, I guess. I didn't know that.
That's the definition right here. I'm telling you right here. Look, I designed a function. My function tests two things. It says, look, if the number that you gave me is greater than or equal to 0, I'll return the same number you gave me. If the number you gave me is less than 0, then I'll return negative 1 times that number.
Okay, yeah, right. And
So if you give me negative 3, I will return negative 1 times negative 3. Negative 3.
okay.
If the number you gave me x and x is negative, I will return negative x.
If the number is less than 0, which means
Yes.
that it's a negative value, I'm going to
Yes.
put another negative on it, which makes it a positive.
Uh-huh.
So it should be.
But negative x can be a positive number, is the whole point. Because if x is negative, then negative x, or if x is negative, then negative x is positive.
Oh, I get what you're saying. So x, intuitively, it's negative, even though we're not mentioning it.
So, when x is negative, then the absolute value of x is negative x. So now we're dealing with negative numbers. So this is equal to the limit as x approaches negative infinity of x cubed minus 2 all over negative x cubed plus 1, which is equal to the limit as x approaches negative infinity of x cubed minus 2 over negative x cubed plus 1. Because negative times negative times negative, 3 negatives is still negative. Okay, so now what's the limit of this thing going to be?
Negative 1.
Negative 1. You see that? So this is equal to the limit as x approaches negative infinity, divide by the highest order term we have in the denominator. So we have x cubed over x cubed is 1 minus 2 over negative x cubed over x cubed is negative 1 plus, not minus 2, minus 2 over x cubed plus 1 over x cubed. Take our limits, we get 1 over negative 1, which is negative 1. So whatever this function is, it has two horizontal asymptotes, one at 1, one at negative 1. And so I don't know exactly what this thing looks like, but here's our 1, here's our negative 1. Whatever it does in between, I don't know if it's above or below. Maybe the author has a rough sketch of this. Okay, yeah, it is. So apparently this function looks something like this in the middle. It comes up like this, it takes off, getting closer and closer to negative 1 there, then apparently shoots up and goes like this. So it looks roughly like that.
That makes sense.
So it has two horizontal asymptotes, 1 and negative 1. 1 is what it approaches if you go arbitrarily far to the right, negative 1 is what it approaches if you go arbitrarily far to the left, which is what we just calculated. Okay. Next. We want the limit as x approaches infinity of sine of 1 over x. Right? Now remember what we ended last week with, or close to last week, close to the end of last week, is if we have the limit of a function, then we can put the limit inside the function. So this is the same as the sine of the limit as x approaches infinity of 1 over x, right? And now, what is the limit as x approaches infinity of 1 over x? 0. What sign of 0? 0. 0, so we're putting 0. Follow that?
Yeah.
Next example, we're doing x times sine of 1 over x, and we're doing the limit, assuming that x goes to infinity again, as x goes to plus or minus infinity, so they want to do both ways. Plus or minus infinity, so we'll calculate both these. Okay. Sometimes you might be a little bit stumped. Common trick, which is the trick that we're going to use for this one, is to define a new variable in terms of your given variable and then solve it that way. So here's what we're going to do. We're going to let x equal 1 over t.
Okay.
Now notice that the limit as x approaches infinity of, how can we say this? The limit as x approaches infinity is the same thing as the limit, I'm saying equal, but they're not equal, these aren't algebraic expressions, but as t approaches 0 from the right, similarly, the limit as x approaches negative infinity is the same thing as the limit as t approaches 0 from the left. So let's make sense of this for a second. Notice that if x gets really, really big, then t has to get really, really small.
Yeah.
Right? So if x over here is 100, then t has to be 0.01. Now, if x were negative 100, then t would have to be negative 0.01. So as x gets really, really big, t gets closer and closer to 0 from the right. As x gets really, really negative, t gets closer to 0 from the left.
Okay.
So, now finding the limit as x approaches infinity of x times sine of 1 over x is the same thing as the limit as t approaches 0 from the right of 1 over t times the sine of t. Which is the same thing as, let me clean up the algebra a little bit and then I think you'll see it. The limit as t approaches 0 from the right of sine of t all over t. And we've calculated that limit.
Yeah.
What is that limit?
Just one.
Just 1, right?
How about the negative?
How about the negative? Well, the limit as x approaches negative infinity of x times sine of 1 over x is now equal to the limit as t approaches 0 minus of sine of t all over t, which is equal to 1. So they're both equal to 1. What does that mean? That means this function, x times sine of 1 over x, as we go arbitrarily far to the right or arbitrarily far to the left, gets closer and closer to 1.
Okay.
I don't quite understand how you got from where the limit approaches infinity to the limit approaches 0.
So look at how x is defined in terms of t. X is 1 over t. So as x gets really, really big, let's look at really, really big and really, really small now. So let's say as x gets really, really big, like 10,000, then t gets really, really small. But positive.
Oh.
And as x gets even bigger, t gets even smaller, but still positive.
Okay.
So, as x approaches infinity, t approaches 0 from the right.
Okay.
Similarly, as x approaches negative infinity, t approaches 0 from the left.
And that's the symbol just for the positive or plus on the top right of the value.
Yeah, this just means we're coming from the right. This just means we come from the left. If we don't have any of those, then we're just talking about the limit period.
Gotcha.
Okay.
How do we know if we should have x equal to 1 over 2? Like, how do you get that?
It's just a common tactic.
Okay.
So, this is typically the only type of substitution you'll do. And notice how it changes our limits.
Mm-hmm.
So that's why it's useful.
Okay.
Okay, now our next limit. So we have y is equal to 2 plus sine of x over x. And this time, we want to take the limit as x approaches infinity. I'll just call this f, makes it fy. Okay. So that's what we're trying to do. Now, be careful which limit we're taking. Notice that limit as x approaches infinity of sine of x over x is equal to what?
1.
No. What we proved is a limit as x approaches 0 of sine of x over x is equal to 1. We did not do infinity.
Okay.
So that's going to be a common gotcha. You're going to go to calculate a limit, and you're going to think, oh, I've memorized this one. And you might accidentally get confused where that applies. So don't fall for that. Does that make sense?
Mm-hmm.
Okay. So we need to calculate this limit. In order to calculate this limit, I want to sandwich this thing. between two values and use the sandwich theorem or the squeeze theorem. I can't remember what we called it.
Sandwich.
Sandwich? Okay. But, so notice, if we're doing it as x approaches infinity, then we can say 0 is always less than or equal to sine of x over x. Let's just do absolute value, because we're also going to calculate the limit as x approaches negative infinity next for this. Just doing the positive one first. And they're both the same. So notice that this is always the case, right?
Okay.
Absolute value of something's always greater than or equal to 0. So this definitely has to be the case. What else can we sandwich this in between? Well, the sine function, what does a sine function look like? The sine function, here's 1, here's -1. The sine function, it looks like this, right? And it alternates between 1 and -1. This is the highest it ever gets, this is the lowest it ever gets. So if we're talking about the absolute value of the sine function, what is the biggest it can ever get? 1. Perfect. So notice that this is less than or equal to 1 over x absolute value. Denominator the same, but replacing sine of x with 1 could have only made it bigger. We couldn't have made it smaller. Because sine of x can be at most 1.
Yeah.
Okay.
Does that make sense? Okay.
Then just simplify.
Huh?
Then just simplify.
Well, now we can take our limit.
Yeah.
So now, what's the limit of 0 as x approaches infinity?
0.
0. What's the limit of 1 over x as x approaches infinity?
0.
0. And so this has to be 0. The sandwich in between.
Okay.
Now, hopefully this one also makes intuitive sense that it was 0. Just looking at it. Sine, this is a number between 1 and -1 always, right? So it doesn't get any bigger than 1. X, as we go to infinity, gets massive. So this whole thing gets closer and closer to 0.
So this looks like it doesn't really matter what the sign was at that point.
Right, it doesn't matter what the sign is. So if we would have done negative infinity, exact same logic, and everything I just erased would have worked as well, because we had absolute values in there.
Now that I think about it though,
So what's this whole limit now?
2.
Just 2. And if I would replace this with the negative infinity, it'd still be just 2.
sine approaches 0, and if it approaches 0, that means it can.
Sine doesn't approach anything.
What I'm
Sine
saying-
alternates back and forth.
What I'm saying is that depending on where you put x, if you need x, you can have it hit 0.
For any x, doesn't matter what x you're talking about, sine of x is always between -1 and 1. So this number is always between -1 and 1.
I know. What I'm saying is that as the sine value approaches 0, it could be 0.000. It could be
Oh, as it approaches 0, then yeah, it hits 0. But as it approaches infinity, it doesn't approach anything. Because it keeps alternating back and
It
forth.
could technically be equal to 1 though.
This is for sure 0. Can't be anything else.
Okay. Yeah.
Okay. Huh?
Couldn't you have divided by all of it by x?
That just gets us our same thing again. So if I divide sine of x top and bottom by x, I get sine of x over x all over 1, which is sine of x over x. Unless I'm misunderstanding it.
By dividing everything in the equation by x, like you did with the polynomials.
Oh, well, we don't need to divide 2 by x. Then we don't have the same thing.
I don't think it's.
I have to divide 2 top and bottom by x, so as we cancel out, we'd be left with 2. In our polynomials, we never changed the value, because what we did to the top, we did to the bottom. It's like if I have 1/2, I can multiply that top and bottom by 5 and get 5/10. It's still the same number. Because I changed top and bottom by the same thing.
Okay.
So yeah, good point. With those polynomials, we were always multiplying the top and bottom by the exact same thing. And so we didn't change the value of the polynomial. We were just writing a different way to make it easier for us to take the limit. Glad you pointed that out. Okay, let's look at another one. We want to find the limit as x approaches 0 from the right of x times our floor function 1 over x. Now we remember what, excuse me. We remember what our floor function is. It rounds down to the closest integer, right? Now, it's really annoying to have the 1 over x in our floor function rather than just an x in there, right?
Yeah.
So, there's another place where the t substitution works out nicely. So if I do x equals 1 over t, or equivalently t equals 1 over x, however you want to write it, then this limit now becomes the limit as x approaches infinity of 1 over t times the floor function of t. Doing this substitution replaces my limit as x approaches 0 from the right with x approaching infinity.
Why do you replace it with x approaching infinity?
Notice that as x gets closer and closer to 0 from the right, t gets closer and closer to infinity.
Yeah.
If we plug in 0.01 for x, we get 100 for t.
Okay.
So that's the whole value of the substitution, is get the terms the way you want them to look and change the limit that you're taking. Because notice now we know how to take the limit of this thing, and now it just remains for us to take the limit of this thing, the floor function. Because a limit of a product is a product of the limits.
Do we even need to do that? Because we know that 1 over t is, the limit of that is 0.
Yeah, we already know that this is 0, but maybe somehow this thing doesn't behave nicely. We're not doing it yet in calculus, but we will be dealing with things where one function approaches 0, another function approaches infinity, and so you have to reconcile that and figure out what exactly it's approaching. So while that happens to work for these early problems that we're doing, you can't always rely on it to be the case.
Okay.
It's just the fact that the author is presenting the material in an organized way. Okay. So this t function, though, this floor of t, what can we sandwich it between? What's the smallest floor of t can ever be?
0.
T minus 1.
1.
Because it can round down at most 1. Right?
Oh, yeah.
When you round a number down, what's the most you could have taken away from that number? 1. You couldn't have really taken away 1, but really, really, really close to 1. You could have taken away 0.99999. Right? So the floor of t, which is less than or equal to t. Oh, we're not going to be able to do that nicely. Notice that this is the case. So now I'm going to make another one, bringing in the 1 over t. So t minus 1 over t is less than or equal to, rewriting this like that, absolute value, or not absolute value, the floor of t over t is less than or equal to 1. You see how since this is true, this is true? Okay, a little bit of algebra on the left-hand side. We get t minus 1 over t is less than or equal to the floor of t over t is less than or equal to 1. Just splitting this up into 2 fractions.
Yeah.
With me?
Yeah.
Take our limits. What's the limit now as t approaches infinity? That's supposed to be a 1. Sorry.
1.
Right? If we split this fraction up, that's t over t minus 1 over t. T over t is just 1. Okay. Have I lost you in the algebra?
Nope, we're good.
We're good? So now, take our limit. What's the limit of this as t approaches infinity?
Would be 1.
1.
1.
Is less than or equal to, we don't know. It's less than or equal to, what's the limit of this as t approaches infinity? 1. So this approaches 1. So this limit is equal to 1. So notice it wasn't 0. And it actually makes intuitive sense that this approaches 1. Why does that make intuitive sense? Because for really big numbers, sorry, this is supposed to be as t approaches infinity, not x. We don't have an x. As t gets really, really big, t rounded down is still really, 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 really big, right? So if you plug in 1000.1 into this function, then you get 1000 over 1000.1, which is basically 1. So it makes sense that this thing approaches 1.
Oh my gosh, no.
Yeah.
Couldn't you have done that from the start? Just multiply x over 1 by 1 over x?
We need to got to deal formally with it. We can't just use a high level intuition. Look, this basically behaves like t, so we're done. Okay. Alright, side example. I'm good for time. Okay, our next example. Find the limit as x approaches infinity of x minus the square root of x squared plus 16. Now notice as x gets really big, this gives us a really big positive number, but this gives us a really big negative number. So the question is, which of these terms dominate? What is this going to get closer and closer to as we plug in bigger and bigger numbers? Because x squared under a square root kind of behaves like x. So it seems close to, we have x minus x. You see that? Okay. So, so we're kind of stuck. We can't just plug in x. What should we do?
I don't know.
What are you always tempted to do when you see that square root?
Find the limit of it?
What should we always try when we see a number minus square root?
You split them up, right?
Now, we should
Square
multiply
root.
top and bottom by x plus the square root of x squared plus 16.
Oh, okay.
Right? Very common. You had to do this a bunch of times on your homework, or this is how you came up with a solution. Right?
Yeah.
Okay. So when we multiply all that out, what do we get? Well, we're going to get an x squared minus x squared plus 16 in the numerator, all over in the denominator, x plus the square root of x squared plus 16. Yep. The x times x gives us our x squared. All our square root terms go out. That's why we multiply this way. That square root times that square root, all this should be negative. Right? Negative this square root times positive this square root. Distribute the negative through.
Okay.
Okay, so this is equal to the limit as x approaches infinity of, our numerator now is just negative 16 all over x plus the square root of x squared plus 16. Okay, so now what does this limit equal? 0. Notice the denominator gets really, really big. We no longer have a minus sign down there. So a really, really big number plus a really, really big number dividing by negative 16.
You could kind of make that intuition just by looking.
Well, you could also do what we say to always do to calculate limit. Divide everything by, what's the biggest term in the denominator? X, right? So divide everything by x, not x squared, because once you take the square root, it's back to x. So I'm going to times everything top and bottom by 1 over x. So we get negative 16 over x, all over x over x is 1, plus, when I bring the x inside the square root, it becomes squared. So we get 1 plus 16 over x squared, like that.
I don't see how you did that algebra.
Okay, we're good with this number?
Mm-hmm.
Good with this number?
Yep.
So it's just this?
Yep.
Okay. So this is the same thing as the square root of x squared plus 16 divided by x is what I'm saying, right?
Yeah.
It would have made sense to you if I wrote that. Okay. Bring it inside the square root means we got square it. So this is equal to square root of x squared plus 16 all over x squared. Good with that? Now split it into two fractions. X squared over x squared plus 16 over x squared. And I think you can see that.
When you brought it into the square root, why did you square it?
When I brought it into the square root, why did I square it? So that when I pull it back out of the square root, it's x again. To
Oh,
maintain
I
its
see,
value.
I see, okay.
It's the same way that 3 times the square root of 2 is equal to the square root of 18. When I bring the 3 inside, I have to square it. Now if I want to pull it outside, I have to take away a square. I have to square root it.
Okay.
Gotcha.
Okay.
Couldn't you intuitively, if you go look at the very first formula, it's just simply a value squared, and then the square root of it, and then so it's a big massive infinite number minus basically a big massive infinite number, which would obviously equal 0.
they could look at this and say, this grows at basically the same rate as this, but this grows positive and this grows negative. So intuitively, those should probably cancel out and come out 0.
Yeah.
Yeah. So intuitively, we expect it to be 0. Okay, so now we're going to find an oblique asymptote, finally.
Okay.
So let's do an example of that. Now, when do we have oblique asymptotes? We have oblique asymptotes when I have this written backwards. Oh no, I don't. Yes, I do. When the numerator is 1 more than the denominator. So when n is equal to m plus 1. I think I have the plus 1 on the wrong side. So the degree of the numerator is the degree of the denominator plus 1.
That's right.
Okay. So, writing it up here, we're doing x squared minus 3 all over 2x minus 4. So notice now, the degree of the numerator is 1 more than the degree of the denominator. So we have an oblique asymptote. We need to take the division and then ignore the remainder. And we'll see why we ignore the remainder here in a second. Because actually, the way that we do this is we're going to take the limit of this thing as x approaches infinity. We're going to see what this behaves like as x approaches infinity. So calculating oblique asymptotes and horizontal asymptotes are almost the same thing.
Okay.
Okay, so let's do this division. So we want to take x squared plus 0x minus 3 and divide it by 2x minus 4. See how that's still the same thing? Just writing out this division.
Okay.
Okay, so how many times does 2x go into x squared?
0.
No, 1/2 x times. 1/2 x times 2x gives me x squared. 1/2 x times negative 4 gives me minus 2x. Okay? Now, subtract x squared minus x squared is 0. 0x minus negative 2x is 2x. Bring down our minus 3. Okay, how many times does 2x go into 2x? It goes into it once. So 1 times 2x, we get 2x minus 4. Subtract those, that minus that gives us positive 1. So we have plus 1 over 2x minus 4. That's our remainder. Okay. So now, we're going to take the limit as x approaches infinity of this whole thing, of 1/2 x plus 1 plus 1 over 2x minus 4. How does this function behave as x gets bigger and bigger? Well, 1 over 2x plus 1, this always behaves like 1 over 2x plus 1. This, on the other hand, gets closer and closer to 0. So we ignore that.
Okay.
So this function, whatever it looks like, there's 1 and a slope of 1/2. So up 1 over 2, like that. So its asymptote is like this. And for really, really big numbers of x, this becomes negligible, so the function just behaves like this thing, which is the equation of a line.
Yeah.
That's why. Let's see, you have the, is that this equation? No, that's another equation. Oh no, that's this equation. So, graphing this whole thing, let's get a rough idea of this graph. So we have its oblique asymptote. Does this thing have any vertical asymptotes?
How do you know if it has a vertical asymptote?
How do we know if it has a vertical asymptote? If the denominator goes to 0 in a way that we can't cancel out with the numerator.
Yeah.
Where is the denominator of this thing 0?
When x is 2?
When x is 2. Notice I could rewrite this if it helps your intuition as x squared minus 3 all over 2 times x minus 2. If we want to factor in. Right? So we have a factor of x minus 2 that we can't cancel out of the denominator. If we could cancel that with something up here, then we would have a hole in our function. But when you factor this in, you're definitely not getting an x minus 2. So that means at 2, not negative 2, at 2, 2 is what makes the denominator 0. We also have a vertical asymptote, right? So we have a vertical asymptote and a horizontal asymptote. So the author gives a rough sketch of what this function looks like. It looks roughly like this. taking limits using our last definition here now. We're going to be actually calculating vertical asymptotes now. So we talked about horizontal asymptotes. Now come look at what these two definitions say, and then we'll talk about horizontal asymptote. This definition says that the limit as x approaches c of f of x equals infinity. Notice that it's x approaching a point. So get a picture of what this thing's talking about. Here's c. So our function, as f approaches c, shoots off to infinity. Our definition here is basically telling us how to get vertical asymptotes. So that's what we're talking about. The limit as x approaches the limit as x approaches c of f of x equals infinity is the same thing as saying that for any massive b out there you choose, pick any really high number b, I can find a delta around c. So this distance right here is my delta. I can find a delta around c such that if x is within delta of c, f of x is above b. So if x is in here, f of x is above b.
Okay.
So that's what this definition is going to say. So it says for every b, for every really big number you can think of, there exists some delta such that if x is within delta of c, then f of x is bigger than b. So f of x can get as high as you want it to get really close to c. Make sense?
Yeah.
So when we do proofs for ones like this, how's it going to work? You're going to assume you're given a b, you're going to find the delta. Very similar to what we've already been doing. Let's look at the other definition while we're at it, because it also makes intuitive sense. The limit as x approaches c of f of x equals negative infinity is logically equivalent to, for every b, there exists a delta such that if x is within delta of c, then f of x is less than negative b. Right? So maybe this function also comes like this. Here's our negative b. Not very symmetric, terrible picture, but you get the point, right?
Mm-hmm.
And so now f of x in here is down there.
And b is always a positive.
Yeah, in both these cases, b is a positive number. Okay, so now let's do some examples. So we are finding the limit as x approaches 1 from the right of 1 over x minus 1. Oh, we're not doing proofs yet, we're just establishing intuition. Okay, so intuitively, what should this get closer and closer to?
0.
As x gets closer and closer to 1 from the right, let's plug in one of those numbers and see what we get. Let's look at 1 over, what's a number close to 1, but on the right of 1? We'll have something like 1.0001, right? And we're going to subtract 1 from that. What's that equal to? 1 over 0.0001. What's that equal to? Big
1
number.
over, yeah.
So, as x approaches 1 from the right, 1 over x minus 1 approaches infinity.
There we go.
Now, what about if we approach it from the left? So now, take a number slightly smaller than -1. So let's look at 0.9999 minus 1 is negative 0.00001, which is negative.
Which is negative infinity.
So this one, now if that's negative, approaches negative infinity. Okay. Another example, still not proof, just an example. Let's see, the limit as x approaches 0 of 1 over x squared. Let's plug in a number really close to 0, like 0.01. So what's 1 divided by 0.01 squared?
100.
Not 100.
0.001.
Still the same.
Same thing, right? 100 squared. Oops.
So it's still infinity then.
So yeah, this is infinity.
Okay.
That's approaching it from the right. We said infinity, right? What about if we approach it from the left?
Just negative.
Infinity.
Negative, so then we would have had a negative in here. Still infinity.
I know.
Because
Still
negative
infinity.
squared is
Yeah.
still positive. Right?
Then it would be an infinity.
So it's infinity both ways. Approaching from the right, you get infinity. Approaching from the left, you get infinity. So if we were to graph x squared, notice we have our horizontal asymptote at 0. That's where the denominator is 0. And it looks like this. And we also have a horizontal asymptote at 0 because the denominator's degree is higher than the numerator's. So we have an asymptote here. So that's roughly what the x squared function looks like. Or 1 over x squared, I mean. Make sense?
Yeah.
Okay. That's a lot of examples. Well, you can go through some of those examples if you want, but they walk you through it. We'll just keep moving on to using the definition now. So now let's do the proof with this, where we actually use our definition over there. So now I want to do a proof. Prove that the limit as x approaches 0 of 1 over x squared is equal to infinity. That's what I'm trying to prove.
Okay.
Okay. 1, let b greater than 0 be given. So you choose some really, really big positive number. Right? What's my job? My job is to find the delta such that if x minus c is less than the delta, sorry, or c in this case is 0, so x minus 0 is less than delta, implies that b is less than f of x. I'm trying to show that for any really big number you pick, I can find a really small distance around 0, such that if x is within that really small distance of 0, it's going to be way bigger, well, it's going to be bigger than that really big number you chose. Make sense?
Mm-hmm.
Okay, so 2, what do we want? We won't bother writing out all the words. What do we want? We want f of x greater than b. So I'm trying to make sure that b is less than f of x. Right?
Yeah.
Well, that will happen when multiply both sides by x squared, divide both sides by b. That'll happen when x squared is less than 1 over b. Okay. Follow that?
You square root it now?
Now we can square root it. So that will happen when the absolute value of x is less than. Square root of x squared is always a positive number. I don't know if we need to keep track of absolute value. It is absolute value, so we'll just keep that. Is less than 1 over square root of b. Square root of b still is just a positive number. You with me?
Mm-hmm.
So now, if x minus 0 is less than 1 over the square root of b, if this is true, this is true. If this is true, this is true. If this is true, this is true. So that's our epsilon, our delta. Delta equals 1 over the square root of b.
Why did you only root b, not the 1 over b?
Sorry, what?
Why did you root only the b and not the 1 over b?
What's the square root of 1?
Oh.
Any other questions? So that's how you prove it. And then definition of a vertical asymptote. These were proving vertical asymptotes. Let's get to the exact definition now. A line x equal to a, some number. So remember, x equal to something is a horizontal line. Y equal to something is my hand movements were wrong, my words were right.
Okay.
Or maybe it was the reverse. I don't know. Say it again. x equal to a gives us a vertical asymptote. X equal to a is a vertical line. Y equal to some constant, typically we say b. Y equal to b is a horizontal asymptote. Right?
Yeah.
Okay. So a line, x equal to a, is a vertical asymptote provided that the limit as x approaches a from the right is equal to plus or minus infinity. Or the limit as x approaches a from the left is equal to plus or minus infinity. So it's a vertical asymptote if, as the function approaches it from either side, who cares, it takes off in one direction or another.
Okay.
And we have 4 possible combinations. The function could be coming in on that point and shoot up like this. It could be coming in and shoot like this. It could be coming in and shoot it like this. And it could be coming in and shoot like this. Make sense? So, for any of those 4 cases, we can still call it a vertical asymptote. So if this is happening or this is happening. Make sense?
Yeah.
All right. We'll do one more example, and then we'll call it good. Find the horizontal and vertical asymptotes of the curve. Well, maybe we'll do another one after this if he has a more complex one. So we have y, I'm going to say f of x. We have f of x is equal to x plus 3 over x plus 2. Sorry. Okay. Where are our vertical asymptotes?
-2.
2.
-2. Where's the denominator 0? -2. So we have a vertical asymptote here. And what about a horizontal asymptote?
At 1.
1. We have a horizontal.
How did he find that again?
The horizontal asymptote, I'm guessing he looked at this rule. He said if
Yeah.
m is equal to n, so if it's the same degree, and then we have a horizontal asymptote at the quotient of the coefficient of the highest terms.
That's
Coefficient
right.
of that's 1, coefficient of that's 1, 1 over 1 is 1. So that's how we got 1. So what does this thing roughly look like? It's going to look roughly like this, I think. All right, let's do another one. Find the horizontal and vertical asymptotes of the graph. And this time it's f of x is equal to -8 over x squared minus 4. Right? Factor the denominator really quick. So we get -8 over x minus 2, x plus 2. With me? All right, where are our vertical asymptotes?
Negative and positive 2.
Negative and positive 2. Now we have a vertical asymptote here. We have a vertical asymptote here. Okay. What about horizontal asymptotes?
Yeah, 0.
0. Y equal to 0. Right? The degree in the denominator is greater than the degree in the numerator. So as a horizontal asymptote at y equals 0. Or take the limit as x approaches infinity, what do you get? 0. Take the limit as x approaches negative infinity, what do you get? 0. Make sense? Okay, so here's where our asymptotes are, and typically we can just kind of test points to get a feel for what's going on here. So let's plug in 3 really quick and see what we get. When I plug 3 into this function, what do I get? I get 8 over 5. Did I do that right?
Yeah.
Yeah.
8 over 5. So when I plug in 3, I get
Negative 8 over 5.
Oh, thank you. Negative 8 over 5. So I'll point down here. So since it's down here, it can't get past these. Well, technically it could get past that asymptote if there was something weird happening. With the standard functions like this, it usually doesn't. So down here, it's going to look something like this. Let's test a point in the middle. Let's test 0. What do we get?
8 over -4, which is -1/2. Or
No.
+1/2.
+2.
0. Negative and negative go out, so we get positive 2. So here, it's like something like that. Well, maybe, let's make sure it's not pointing down. Let's plug in 1 real quick and make sure it gets higher. When we plug in 1, then we have 8 over 1 minus 4, which is 8/3, right? 1 taking that negative. So it gets higher.
Yeah.
Notice if I plug in a number really, really close, a little bit less than 4, then this minus this is going to be a really small negative number. Take that negative, really small positive number. 8 over that, so it's going to shoot up.
My back's killing me.
That's fine. So we have this picture, test point over here now. Let's test negative 3. Negative 3 gives the same thing as 3. This is an even function, and so it's like that. So it looks roughly like that.
Okay.
Okay, so that concludes this section. Hopefully you can hear me when you go back and watch it.